Work pumping liquid. Let's discuss pumping liquid from a container. Pumping a liquid out of the top of a tank requires work because the liquid is moving against gravity. To calculate this, we imagine the work required to lift small slices of liquid up and out of the tank. So we are lifting a series of masses against gravity and allowing the liquid to spill out once the top is reached. What varies in these systems is the volume of each slice and the distance each slice needs to be lifted, measured by taking the total height and subtracting the present height of the remaining liquid y. So in general, for emptying a tank, the work formula is the integral from y equals a to y equals b of f of y dy. But let's break that down a little bit further and then look at this diagram over here. So what we're going to do is we're going to integrate wherever the liquid exists. So here I have this conical tank and I have put the origin right at the very bottom of the cone. And so what we're going to do is we're going to integrate from y equals a to the very top of the tank, y equals b, because this tank is totally full of water, so we can only perform work on the actual liquid. I assume it was water. And so what we're going to do is we are going to have to represent the distance that each slice is lifted. So we're going to focus on a particular slice at location y. And so how far does that slice have to travel? It's going to travel wherever the top of the water is spilling out from minus y. So in this case, the very top is at a location of B. So that distance lifted is going to be B minus y, or wherever the spout is, minus y. And then the increment of force is going to be the weight of the liquid, because liquids have different densities. So we're going to have to include the weight of the liquid times the volume of the slice. And that's the part that's going to take a little bit of thinking about. So in this system, in this tank, if it looks like a cone, if we take a slice, that's going to create a really, really thin cylinder. So if I think about taking a cross section or a slice, it's going to be a cylinder. So I'm going to have to figure out a way to represent the volume of that slice. So again, it's at a location of y and it has a little height dy. And so because the volume formula for a cylinder is pi r squared, I'm going to need to think about what the radius of this particular slice is going to be at any given y value. So we're going to see examples of this in practice, because each slice could be a different shape. In this case, it's a cylinder or a disc if we make it infinitely thin. But there's lots of different examples, and we want to just understand the concept here that this is the structure of the work formula we're going to be using. Let's jump into an example. A circular swimming pool has a diameter of 24 meters. The sides are 5 meters high, and the depth of the water is 4 meters. How much work is required to pump all of the water out over the side? Note, the density of water is 1,000 kilograms per meters cubed. We'll start by sketching a diagram. All right, so here I have a right circular cylinder. I have the diameter is 24 meters, the height is 5 meters, and then the height of the water is only 4 meters. So the water doesn't go all the way to the top. So let's go ahead and start to set up our integral to calculate work. So work is going to be the integral from y equals, in this case, if I think about the x-axis as the bottom of the pool, then that means my limits of integration are going to extend from y equals 0 to y equals 4. We only integrate over where the liquid is present. So again, if the bottom of the pool is the x-axis, that's y equals 0. The depth of the water is 4 meters, so that means that the limits of integration extend from 0 to 4. And then what we're integrating, that force, F of y, has those three components. So we have distance lifted times the weight of the liquid times the volume of the slice. All right, well, let's go ahead and draw a representative slice. So when we think about a slice or a cross-section, we're talking about essentially sort of a circle, and that's not a very good circle, but it'll do. And it's at a generic height of y from the x-axis, being the bottom of the pool. So what's the distance lifted by a generic slice? Well, it's always going to be the height of the tank. So what's the highest point that the water needs to overflow over? So that's going to be 5 minus y. So the distance lifted is going to be the quantity in parentheses, 5 minus y. And let's go ahead and attach some units there for a second. That distance is going to be in meters. And then we have to calculate the weight of the liquid. And so that's why this note is given here, the density of water. So because we are given the density of water is 1,000 kilograms per meters cubed, I'm also going to have to include gravity to that to find the weight. So it's that difference between the fact that pounds already includes weight, but if we're given grams or kilograms, or we're working in the metric system, we have to multiply by acceleration, which is gravity. So this applies when grams, kilograms, we're going to need to take into account gravity as 9.8 meters per second squared. So the weight of the liquid is going to be the density of the water, which is 1,000 kilograms per meters cubed. So I'm going to go ahead and put in 1,000. And below it, I'm going to put the units. So that's kilograms per meters cubed. And again, we have to include gravity here. So 9.8, and that's meters per second squared. And then finally, what we need is the volume of the slice, dy. So dy is the thickness of the slice, essentially. And we know that because we're doing an integral, the thickness of the slice, so dy is this little thickness here, the thickness of the slice gets infinitely thin because we're computing an integral. So the volume of the slice, well, the slice is essentially a circle, right? It's just a circle. And the cross-section area, essentially, if we make it infinitely thin, is not varying. So across this whole tank, the cross-sections are always going to be a circle with the same area each time. So here, it's kind of a nice volume of a slice formula. So we have, I'm going to pull out that individual cross-section for a second. So let's think about just this like individual cross-section. The height is dy, and then the circle for the area of like the base there, so that area is pi times the radius squared. Well, the radius is going to be 12 because the diameter is 24. So the radius is 12 meters. So my area is 144 pi meters squared. So that's the area of the base, and then the height is dy. So that's what we're talking about, like the volume of the slice. So we need the cross-sectional area and then times dy. But again, that dy is the differential, so it's getting infinitely thin as we integrate over 0 to 4. So the volume of the slice dy is constant. It's 144 pi, and then dy, that's the height. So that's base, which is the area of the circle, times the height dy. And the units of 144 pi were in meters squared. So I was trying to just kind of separate here this individual cross-section, which is its own little cylinder, and the volume of a cylinder is the area of the base, well, the base is a circle, so the area of the base times the height. So the area of the base is just a constant 144 pi, and then the units there was meters squared. All right, now that that cross-section is out of the way, let's talk about the units and make sure everything checks out there. I have meters and meters squared on the top, that's meters cubed, and a meters cubed on the bottom. So that means those are going to cancel out. Meters squared is going to cancel with the meters cubed on the bottom. So the units that I have remaining for this entire big quantity inside here of the force is kilograms times meters per second squared. which is exactly newtons, and that is the unit of force here in the metric system, which is what we're using right now when we're talking about these units of measure, meters and so on. So this checks out. If we were talking about feet and pounds, we would need this all to work out to be pounds, but here it works out because the force is in newtons. And then y equals 0 to y equals 4 is in meters, so when we compute this integral, we will get out Newton meters, which are joules. So now the units are just a great check to make sure that you have included all of the different pieces that you need, but then we can sort of drop the units when we now go to integrate. And we can pull out all of these values, 1000 times 9.8 times 144 pi, all of those are just a coefficient. So it's just a number that's multiplied times 5 minus y. So I can pull it out of the integral completely to make my integration simpler. And if I multiply it all together and I pull it out to the front, it's going to be a really big number. And I'm going to go ahead and tell you that number is 1,411,200 pi. And then the integral from 0 to 4 of 5 minus y dy. So don't multiply the pi in. You can go ahead and leave it in terms of pi, this coefficient in the front. And now all we're integrating is 5 minus y. So that's going to be 5y minus y squared over 2 evaluated from 0 to 4. And of course, all of that is times that 1,411,200 pi. And so we'd, of course, plug in the 4 into each y. So we have 5 times 4 minus 4 squared over 2. Thankfully, plugging in 0 is not going to do anything there. And if we multiply all of this out, here's what we get. 16,934,400 pi, of course, we're going to leave it in terms of pi, joules, or Newton meters. So it is primarily the setup of these problems that tends to be tricky, but it's helpful to think about that these three pieces are required: the distance lifted, the weight of the liquid, and then the volume of the slice dy is going to be probably the hardest part. This one was an easy example because the slice was a constant sort of volume each time, right? So that area was just always, it didn't matter where we were between 0 and 4, that cross-section just had an area of that 144 pi. But we'll see examples where that cross-section varies. All right, there is kind of a little bonus question, an add-on question to the previous example. What if the tank had a lid and a 2-meter spout added to the top? How would this affect the setup? So now this water that's being pumped out of the tank has to get up and out of this 2-meter spout. So here's the nice thing. Not much would change. So our work formula would still be the integral from y equals 0 to y equals 4. So we're still just integrating over where the liquid is present. What's actually going to change here is the distance traveled. So our cross section, which was at a height of y, now it has higher to travel. So now it has to get up and out of this 2-meter extension and travel a total of 7 meters. So the difference is that our distance traveled is going to be 7 minus y. But other than that, everything else is the same. We're still going to have that 1,000 times 9.8 for gravity, and then that cross-section, which was 144 pi, pi times 144 is the same thing, dy. So the only thing that is going to change on this problem is the height that that cross-section has to travel, the distance that it has to travel. And now in this example, we have a right circular conical tank of altitude, which means height, 20 feet, and base radius, 5 feet, has its vertex at ground level and axis vertical. So we essentially have that sort of ice cream cone situation I was talking about earlier. if the tank is completely full of water, find the work done in pumping all the water over the top of the tank. Note the weight density of water is 62.5 pounds per feet cubed. So this problem we are now dealing with feet and pounds, so that's just something to sort of keep in mind. And so we have a diagram started here, so I have sort of this triangle that's like the two-dimensional representation of the three-dimensional cone, and we'll label it with the values that we were told. So the height of this tank is 20 feet, the radius is 5 feet, and we'll say that the slice is at a height of y. And then we'll pretty much get started on setting up the integral. So to calculate the work, we're doing the integral from y equals 0. So the water starts at the ground level, which we're going to assume is the x-axis, so that's y equals 0. And since the tank is full of water, the limits of integration are going to be from y equals 0 to y equals 20. And then we have those three parts that we need to fill in. So we need the distance lifted, and so we're focusing on a slice. So the distance lifted of this slice, which is at height y, is going to be the total height of the tank, which is 20 feet minus y. So we're going to have 20 minus y. And then what we're going to need is the weight of the liquid. Well, the good news is that because we are given weight density in terms of pounds, we don't need to additionally include gravity. So our weight of the liquid is simply 62.5 pounds per feet cubed. So I'm going to put 62.5, and let's put the units on there just like last time, pounds per feet cubed. 20 minus y, that was in feet. And then what we're going to need this time is the volume of the slice. But the volume of the slice isn't constant anymore. So it definitely depends on the y that you choose. So if I were to choose a smaller y value than the one that's constructed here that's more towards the top, if I were to take a slice more towards the bottom, that volume would be less. That would be a lesser amount of volume than towards the top, because of how a cone starts really narrow at the bottom and then widens towards the top. As opposed to that previous example, each circle was the same area. So when we had that height dy, so each volume, each disk was the same as I stack them up vertically. But here, these disks, although they are still little cylinders, the radius of each cylinder is different. So let's sort of take out one of those cylinders and sketch it and sort of think about that for a second. So if I take out sort of one of those individual little cylinders here, the volume of that cylinder is pi, and then we're going to need r squared h, right? But h is dy. Dy is that little height. So pi r squared dy. It's just that this time, what's r? So r is not a fixed value like it was on the previous example, where r was just that fixed radius every single time. R is going to vary, and it's going to vary as a function of y. I need to essentially find r by doing right minus left. So thinking about sort of the right side of this cone as a linear function, and then thinking about doing that linear function right minus left, but left is just the y-axis here, so that's just minus 0. So let's think about what the equation of this line would be. Well, the line is passing through the origin. If I think about this as the y-axis straight down the middle, and so I'm really just in need of the slope to write this line in slope-intercept form, right? Y equals m times x. Well, what's the slope? I'm going up 20 units from the origin, that's the height of the cone, and I'm going over 5 units. So up 20 over 5, 20 over 5 is 4. So this is y equals 4x as a linear function. So that's the equation of this line as a function of x. But I need everything to be in terms of y. So I need to do right minus left here. So instead of thinking about this as y equals 4x, I have to think about it as y over 4 is equal to x. Divide both sides by 4. So this radius here is y over 4 minus 0. That's going to be this radius as I travel from y equals 0 to y equals 20. It's getting bigger each time. So that's what's going to go inside here. Again, when I think about sort of the volume of the slice was a little cylinder. The area of a cylinder is pi times the radius squared. The radius was not constant. The radius is varying. So I need to replace that with y over 4, technically minus 0, right minus left, squared dy. So I'll fill in over here, r was y over 4. All right, so that's what's going to come over here as the volume of the slice. So we have pi times, let me go ahead and start to simplify this a little bit. Pi over 16, 4 squared is 16, and then y squared dy. And the units of pi over 16 y squared is going to be feet squared. So dy is that height, right? So this part right here, pi times y over 4 squared, that's just the area of the base, which is the area of a circle, times dy. So this portion right here, pi over 16 y squared, has units that are feet squared. So what's going to cancel in terms of units? Feet and feet squared will cancel with the feet cubed on the bottom, leaving us strictly with pounds. And that's what we want to happen. We want to be integrating a force, and pounds is a force. Now this time, the only thing we can pull to the front is 62.5 pi over 16. So that's the coefficient, but y squared is a variable. I cannot pull that out. So in terms of actually integrating this, I can take out the 62.5 pi over 16, and then the integral from 0 to 20, and then the y squared times 20 minus y. The best way to integrate that would be to distribute the y squared. So we're going to have 20y squared minus y cubed dy, the differential, and 62.5 pi over 16 times the antiderivative here is going to be 20y cubed over 3 minus y to the 4th over 4, and that's evaluated from 0 to 20. And of course we're going to plug in 20 into both of those y's. Plugging in 0 is going to just make those terms go away, and so the overall answer here ends up being, here I did go ahead and multiply in the pi to arrive at 163,624.624, and then we would have foot-pounds as our units. And these problems would definitely require a calculator if actually evaluating, but not if you're just setting up, because the real ugly numbers come with the evaluation of the definite integral. In this example, we have a rectangular swimming pool is 20 feet wide, 25 feet long, and has a 3-foot shallow end and a 6-foot deep end. It is to have its water pumped out to a point 2 feet above the current top of the water. The diagram shows a side view of the length of the pool. Set up the integral or integrals needed to find the amount of work performed in draining the pool. Note the weight density of water is 62.5 pounds per foot cubed. All right, let's look at the diagram. Here's the side view of our pool, which is 25 feet long. The shallow end is 3 feet deep, and the deep end is 6 feet deep. And we're told that the swimming pool is 20 feet wide. So since this is a side angle view, we can't really see the depth. So we're going to add that layer of depth to help us understand what's going on here. So we're going to say that it is 20 feet deep. And now we want to think about the cross sections, which are going to be different at different values of y. So this is actually going to take two separate integrals. So if I think about the cross section down towards the deep end of the pool, the length of that cross section is hitting two different functions essentially. It's hitting the left side of the pool and then it's hitting the slanted portion where it goes from shallow end to deep end. But if I go towards the top of the pool, then our length of the cross section is just going from one side of the pool to the other side of the pool. So we're going to actually need to split this up into two separate integrals, right where the shallow end starts to head down to the deep end. Now we have to put our origin somewhere. We have to put our vertical and our horizontal axis somewhere. And we have, I wouldn't say two different choices that are, we actually have more than that, but I'm going to go ahead and say we have two kind of obvious choices here. I'm going to put the horizontal axis at the very bottom of the pool. But where we put our vertical axis is going to affect things. And I'm not going to say one is better than the other, but I prefer one over the other. So instead of putting the vertical axis on the very left side of the pool, where I'm going to put my vertical axis is actually right at this corner here, where it starts to rise out of the deep end of that pool. And the reason is because I'm going to need to find the equation of this slanted line right here. And if it passes through the origin, then the equation of this line is a lot easier to find. So I'm going to go ahead and again put my origin kind of right there at that corner, and then I'm going to go from there. So let's go ahead and try to find the equation of this line. If the entire length is 25 feet and this deep end is 10 feet and the shallow end is 10 feet, this distance across right here is going to be 5 feet. So this distance right here is 5 feet. So this coordinate point is going to be at an x value of 5. And then let's talk about the height here. So if the shallow end is 3 feet and then the deep end is 6 feet, then right where this starts to go down to the deep end, that's going to be at 3. So I'm going to go ahead and say that the y value here is 3. What is the equation of this line? If it passes through the origin, I just need the slope. So I'm going up 3 over 5. So this equation is y equals 3/5 x. But I want it to be in terms of y, so I'm going to say the equation is actually x equals 5/3 y. That's the equation of this line right here. All right, so now let's go ahead and start to set up our two work integrals. So first I'm going to calculate the work done pumping the liquid from the very bottom of the pool out a spout that is 2 feet above the top of the pool. So I'm going to remind myself that it's 2 feet above. I'm going to draw myself a little spout 2 feet above. So my first integral, I'm going to call it work integral 1. That's the integral from y equals 0 to y equals 3. So again, I'm pumping the bottom part of the pool here from 0 to 3. And then I need the distance lifted of a particular slice. So if I'm focusing on a slice down here at y, the distance traveled is going to be this very top height up here, where the top of the spout is, which is a total of 8. So the top is at 8 feet. So we're going to have 8 minus y. And then I'm going to need that weight density of water. So I'm going to put that 62.5. And then I'm going to need the volume of the slice. Well, a slice here is actually going to be a rectangular prism. I'm going to draw it sort of below. So at that y value, I'm going to have this rectangular prism slice going on where the height is dy and the width is that 20 feet. So all the way across is going to be 20 feet. And then I need the length. So I need this L length right here, which is going to be found by doing right minus left. So the right side, we calculated that line to be x equals 5/3 y. So this length right here, let's call it L of y, is 5/3 y minus, so right minus left. So this left-hand side, this equation right here, is at y equals -10. This distance here is 10. So 5/3 y minus -10 is 5/3 y plus 10, right? So this distance is this 10 feet over here plus this little distance here, which is 5/3 y. So 5/3 y plus 10, that's the length. And then the width is 20 feet. And then the height is my dy. So right here, what I'm going to have is I'm going to have 5/3 y plus 10 times 20 dy. So that is the work required to pump out the bottom portion of the pool out of the top of this spout. And then we're going to have another integral for the work required to pump the top of the pool out. So this is going to be working on the liquid between y equals 3 and y equals 6. The distance this slice is going to have to travel. So now let's look at this slice here. I'm going to call it another y value up here. Let's just call it y1 for a second. So here, this slice is also going to have to move 8 minus y, so that stays the same. Then we're going to have 62.5. And then let's talk about the slice up here. So that's actually going to have a constant length. So that length up here, let's call that L1, that's always just going to be 25 feet. So the prism up here is going to be 25 by 20 and then dy. So we don't actually have to sketch that out. Hopefully we can kind of see what it is. So it's going to be constant there. It's going to be 25 by 20 dy. So what is the total work required? We're just setting up the integrals, let's remember. So we're just going to say W1 plus W2. So the total work required is W1 plus W2. We set it up as two separate integrals, and then we'll just go ahead and say that it's represented by this expression instead of rewriting both of them again. And the units of the final answer here, we were looking at feet and pounds, so it's going to be in foot-pounds.